Lovely to have you all here. I mean, this is great. It's a bit cosier than normal, which is, I don't know if that's going to be good or not. It makes it easier for me to talk to you, and because we're recording everything, Mike is going to be Mike. So that's the only reason. I mean, he's loud enough to be heard by everybody anyway. Anyway, housekeeping. Most of you have been here before, but those who haven't, there are no planned fire alarms tonight. The room there, and it's very difficult to get through that one. So if there's a fire alarm, it is a fire. Basically, follow me. But no, basically, out to the lifts and round the lifts is one set of stairs down. Through where we came in, right to the other end, there's another set of stairs the way down, and it's all very easy. Other bit of housekeeping, if we've got a sign-in sheet and we've got some name labels, if you haven't done the sign-in, or if you haven't got a label, or both, please do so. It's quite important for the group because it's part of actually showing that we are doing some stuff of interest to people, and that's really quite important. So without further ado, as most of you know that are here, you'll know that we had our planned speaker was unable to make it tonight, and so very much at the last minute, Mike Small has stepped into the breach to do something completely different from what we had originally planned, but I'm sure it's going to be great fun. I'm not going to spend ages on this, but Mike's stuff and Mike's CV and what he's going to be talking about is all on the sheets that are on the chairs, so you can read it yourselves. But I've known Mike for many, many years, and he's a great fun guy. And I'm sure what will go down will go down. Are you taking questions during?
Well, usually people heckle me.
Yes.
And I respond.
Yes. So, but if you are going to ask questions, can you do it loudly so that it can be picked up for the recording? We don't have a roving mic to do this, so just shout.
You have got a roving mic.
Yes, indeed. So just shout at Mike loudly, and that will work. That will work well. What else have I got to say? The other sheet on there is the last 4 we've got of this season. Again, they're all very different, and they should be quite fun. I'm now booking next season, which is September through July next year, and I've already got 5 speakers lined up for that, which is great. But if anybody else is interested in bringing forth their infinite wisdom, which I'm sure we all like to think we have, that would be extremely good for the group. But on that note, I think I've blathered enough. Mr. Mike Small.
Thank you. So this is kind of a fortunate.
Are you switched on?
Am I switched on? Yes. No, I'm on mute. Is that better? I think that's.
That is a bit better. Yeah. Could go a bit further up your tie.
Okay, well, it's just trying to get it recorded, isn't it?
Yeah. Well, the mic's working.
Which one?
There is only one.
Okay, so this is a fortunate sort of intersection of the trajectories of the planets, because as an analyst, what tends to happen is that we have to speak about what our customers want to speak about. And now everybody's stopped talking about blockchain. They've started talking about AI. This is the latest buzzword and the latest piece of stuff that everybody's buying, which is an emerging technology that has really been emerging for at least the last 70 years. So now, from a perspective of risk management, clearly all these new technologies introduce some element of risk. So tonight what I'm going to try and do is to talk about what AI is, because there's a lot of myths about what it really is, and there's also a lot of myths about what are the risks around it and where we are. And so I'm hoping to be able to put AI into some kind of perspective. Now, because of my concerns with all of the technology which we have on the desk in front of us here, there is a YouTube video which I want to show, and because of the difficulties of making this work in this complex environment, I've left that till the end, so that it doesn't work. we don't lose too much. Now, so I work for an analyst company, and an analyst company, we analyse the markets for technology. And as I've said before, there are two kinds of people in front of us. The vendors who are telling us that this is the next best thing since sliced bread and no one can do without it. And the customers who've heard all of this and really are uncertain as to what it is that they want to use. So we try to moderate between these two. And so I write reports, I speak to customers, and we also give advice to vendors. That's the summary. And the first thing is, what is AI? Well, it's artificial intelligence, and even the word intelligence has all kinds of different meanings. You know, there is security type of intelligence, and there is the intelligence that we see in the way people behave. And I don't really see a lot of real intelligence, never mind artificial intelligence. So I've basically tried to encapsulate this in this, and I was only today listening to someone. It took him several paragraphs to try and say what AI is. In a sense, it is an attempt to simulate human abilities and to give them superhuman powers using computing. And in a way, we all know how sentient beings behave. There is some kind of input which is put together with all of your experience, and it results in actions. And so AI has been used to cover things like robotics as well as decision making. But typically what I'm talking about today is more about decision making. And so in effect, what we are trying to do is to replace calories with kilowatts. In effect, we're going to use computers to do it, and I'm going to try and talk about how that might happen. So, in a sense, this means we have to capture knowledge. And it's very interesting, because if you look at the process and the history of AI, then you can sort of see the different phases of the technologies and the way that it was being used. And kind of it starts off with philosophy and this wonderful word epistemology, the understanding of beliefs and knowledge. And so the philosophers try to capture what we know in terms of syllogisms and logical statements. Well, in fact, that goes so far, but then there's another world which can be captured in terms of mathematics. And mathematics has, if you will, replaced a lot of the philosophical view of the world when we start to look into things like the modern views of physics and so forth, where the only way we can model this strange universe that we live in is by building mathematical models that sort of kind of confound us by making the world appear to be a very strange place indeed. And then, as well as all of that, if you want to look at how people behave, then you go into other dimensions of science, and looking at biology and psychology is quite important, because the way in which we see things, i.e. how vision works and how perception works, is a combination of science and psychology. So all of those things, in a sense, are important if we are going to simulate the way in which people perceive the world and the way in which people behave. So AI as an idea is not new, and certainly, you know, for centuries people have tried to build automata that represented what people do. But the AI that we know today sort of came from mathematics that started off in the 1940s, and it was a thing that was called threshold logic. So that mathematics set in train the essential foundation for what we now know as artificial neural networks. Now, in the meanwhile, all kinds of things were described at the time as being to do with artificial intelligence. When Ferranti, the Ferranti Mark I, the Manchester computers, was playing checkers or chess in some primitive way, at the time in the 1950s, this was conceived of as being intelligence. Interestingly, in the 1950s, there was a sort of fork in what happened. Some people went off down the world of neural networks and trying to simulate the brain, and at the same time, other people were trying to say, well, mathematics is very good, computers work with numbers very well, but what in fact we need is the ability to manipulate symbols so that we can build philosophy, or that we can understand language and semantics. And that led to the building of this thing called Lisp, which is a very interesting Lisp-based processing language, which was the basis for a language interpreter based on Lisp. Now, when you start to try to interpret language based simply on the words, you end up with some very interesting outcomes. And one of the famous experiments was what you do is you feed in something in, shall we say, English, you translate it to another language like Russian, and then you translate back what it is that was in Russian. And the famous example of that was that somebody translated into Russian, the spirit is willing, but the flesh is weak. And when this was translated back from the Russian back into English, it became, the vodka is good, but the meat is rotten. So, in a sense, the point there is that language is more than just symbols. It's something about the culture, it's something about the knowledge that we've acquired, and metaphor and idiom and all of these kinds of things have to be brought into place. Now, how I got involved in this was that in 1982 I was standing in the wrong place. I was working for a company called ICL, and the Japanese had published this thing called the 5th Generation Computer Project, and everybody in Europe went cold because the Japanese at that time had just stolen the market for mainframes from IBM and everywhere by building better mainframes cheaper, more reliably than the other manufacturers. And so suddenly the Japanese were going to take over everything else in the computer industry. So of course the government poured loads of money into it. And well, that was a big success. In fact, in 1992, the New York Times produced an article which was called "The Generation That Never Was," in the sense that the Japanese never actually produced the 5th generation computer. But in the meanwhile, it did get a lot of funding into the development of these technologies. It led to this thing called the Elbe project, which covered a whole series of different things, and I was involved in this thing called knowledge-based systems. Now, I'm going to sort of pick on this because this represents what happened in the 1980s, and it was, you know, useful. It had some outcomes. And so to look at some of the things that didn't work very well. Well, first of all, one of the systems we were working on was that the government said, we really need something to help to deal with the interpretation of social security rules, because every local office does it in a different way. And there's all of this gigantic amount of paperwork which is involved in that. So there was a lot of work done on that, but this is one of these sort of poison chalices, because whatever you do, it becomes more involved in politics than it does in technology. And so there was a lot of interesting stuff was created for that, but it wasn't what was ever used. The other system was paramedical, which was a recognition that there was an opportunity to try and help with the diagnosis of diseases. And again, that was written in a language called Prolog, and it went somewhere but didn't go very far. Now, Prolog was a language which was really good for expressing logical statements, and you wrote them literally as syllogisms, and basically the system then worked out what the result of that was. And that led to an amazing thing, that we sold against worldwide competition a system for laying out containers in the docks of Hong Kong. Now, anybody that knows Hong Kong it is and it was a major interchange port, and there is a really significant challenge that ships come in, unload tons of containers, and then other ships come in and pick up some of these, and actually optimizing how you lay out these containers so that it's easy to get them is extremely complicated. But there are rules to do with doing it, and the problem is that people's brains aren't good at implementing those rules, and so our Prolog system was able to do that. The other two systems also were based on rules. This S39XC was a configurator. Now, many products have to involve bringing together lots of components, each of which has to be specifically chosen and specifically configured to make it fit with all of the others. And if you get it wrong, it can be extremely expensive. Anyone who has had a kitchen fitted will understand that, because a kitchen, the designer comes along, says everything will be delivered, and 98% of what you need is delivered. That 2% is what means that you then live in a disaster zone for 2 weeks or 3 weeks, trying to get these things that are missing. So once again, it's an example of where there are rules about what you need. The rules are often quite complicated and people get them wrong, or the logistics don't work. And the third one was this capacity management system. And we will come back to this because this is something that has recurred. And this is interesting for another point of view, in the sense that what we did in this was we captured the best state of knowledge about how to work out how to tune your mainframe. And we thought that was what people needed. In fact, when we sold it, we started to get these calls from salesmen who said, we really love your product because we've just been able to persuade customer X to upgrade their mainframe. And we've been telling them for years that they needed a bigger memory or a bigger whatever it was, and they didn't believe us. But when your computer system said, you need this, they believed it. And so somehow or other, although this was just basically implementing rules, there is another dimension to all of this, which is the trust people have in either a salesman or a computer system. And just as a corollary, I work at, also as a lecturer at Salford University, and there we have a driverless autonomous van. Literally, it is driverless. It's sort of a little test that's going around the campus, and it moves things for you. And we noticed that students walk in front of it. because they know it will stop. Whereas if it was another student in his car, looking at his phone and distracted with whatever his girlfriend is going to be doing, the chances are they'd be run down. So the interesting aside from all of this is people's behaviour with these systems. So what's happened since then is that we've had this industrialisation of information. And in a sense, the reason why AI has come up to the fore is for a number of reasons, one of which is that we now have almost limitless computer power on tap. And we also have vast amounts of data, and why we need that is we're going to come back to. So not only does the cloud provide the data, the storage, the data and the access to it, but it also collects more as it's being used. And it turns out that the data miners, the big Googles and so forth, need AI to try and make something of that data. And I will go into this in a little bit more detail as we go on. So the cloud has brought together the things that are going to move the technologies that we had in the 1980s into a more useful and usable form. So, and here's the example that you can, using Amazon, you can get, it costs $100 per million AI predictions using Amazon. That's kind of the price that you can get this kind of stuff from using the cloud. And you do this based on a large amount of data and so forth. Now, when you look at the technologies that underlie this, there are really these layers, and a lot of the way in which AI is being used today is really about data analytics. And it starts off at the bottom that the stuff that you're using called AI today is really founded on mathematics. And mathematics starts off with statistical systems at one end, and neural networks are nothing but implementations of algorithms based on threshold logic. You can then sort of take that a layer above, and these are basically things that you can do with algorithms, and deep learning is nothing more than multiple layers of neural networks. And on top of that, you can actually build things like computer vision and natural language processing in a much better way than you could just using symbolic analysis. So machine learning is the thing that has really made the difference. And machine learning is a different way of writing programs, and it's important because of this. That at the moment, if you sort of decide you want to do something with this data that you've got, what you do is you go to a data analyst or you go to a programmer and you say to the programmer, here's some data, I'd like you to find something out about it. And they say, okay, we'll do that, and you write a program. And then you say, well, actually, there's another way we could look at this data. Can you change it? And they say, oh dear, well, we need a bit of research. We'll do some more program. And basically, it's very expensive and it's very slow. So the theory, the idea behind this is it would be much better if what you could do is train a system to be able to analyze data in certain ways. And then all you ever have to do is to throw new data at it, and somehow or other it sort of modifies itself or it improves itself to do what you want. So it gets over the programming delay hurdle. And the way in which this starts off is you get some data that you know contains information that you want to be able to extract from it, and you can say, here is this data, and this particular bit of data represents this kind of thing, and so you have curated it and tagged it, and you feed it into this learning system that then in fact produces an algorithm which, when given other data, will come up with the right results out of that.
Mike, where's the magic wand in this?
Well, I'm going to tell you what there is a magic wand. It's basically all mathematics. That's the magic wand.
So if you get your algorithms wrong,
So,
everything's wrong.
well, yeah. So the point is that's the perceptron. The perceptron was invented, I think, in 1957. So it's not exactly, you know, kind of cutting edge new technology. So what do you do with this? Well, what you can do is you get a data set. Now that is a data set. And there is a gigantic data set produced by NIST, which is called MNIST, which is of all the combinations of the ways in which people write numbers. And I don't know, 500,000 or something of these things. So there's a training data set. You know from this data set that all of those are zeros, and there are pages and pages and pages of the way people write zeros. So you've got it tagged. You've got curated tagged data. So what you basically do is you feed that data into this system, and what you have to imagine is that there is a convergent algorithm which allows you to adjust these weights. So, you know, let's say you're feeding pixels in, and these pixels come in, and the pixels contain a matrix of dots of ones and zeros, and each one of those ones and zeros will have weights associated with them, and that you have this function which is a threshold function that says with the right weights and the right threshold, all of these things that are marked 0 will give you the answer. That means it's a 0. And the mathematicians, the clever little fellows, have proved that you can write an algorithm that will in fact converge on the right values for the weights and the threshold, providing the training data is linearly separable. And that's what that little graph there means, i.e. that if you put them on a two-dimensional axis, that there is a straight line. Well, actually, in most of the real world, there isn't a straight line. There's actually a wibbly line. And so there's lots and lots of evolution of these algorithms for convergence to do with whether or not you have a wiggly line and so forth.
Is it not the case that for that perceptron, it's taken each pixel in complete isolation, it's doing no processing with its neighbours?
Yes, and so you can then actually say that you can have other algorithms that involve looking at what neighbours are and so forth. So I've just basically described the simplest, most fundamental way of doing this. And this is something that, you know, people were doing this in the 1980s, and I've got a story which I will tell you in a minute about this. They were doing this before. So in order to actually be able to do this realistically, you need a lot of kilowatts to be able to get the answer. And so here is an example of how this is done. This is called deep learning because there are layer after layer after layer of processes that are going on which start off enabling a picture like that to come up with an identification of a dog and a cycle. And so in a way this is getting closer to the way the actual human eye works. And the human eye, if you look at how people see things, and I'm not an expert on this, but I do know because I've had children, and children have to have good vision in certain points of their growth, because within the eye there are layers that are learning to perceive things, and they only learn at a certain age. So for example, being able to distinguish right angles and certain kinds of shapes and so forth is something that are done by the different layers and only can be learned at a certain point in the child's development. And this is also proven because if you find people who, through some disability or whatever, were blind until they were adults, but then by some magical medical treatment, actually have vision restored. They have vision, but they don't have perception. If you see the difference, that they can see something, but they can't necessarily tell you that the clock is round. So actually, to do this is very difficult. And what has happened is that for certain kinds of problems, most of the large software vendors or cloud vendors now will sell you services that are pre-packaged, that you basically just can adjust to do what it is that you want. So you will find that they will give you a pre-programmed vision thing, they'll give you a vision thing which you can adjust, and then they'll give you a toolkit, and there are lots of toolkits that are around where people can effectively cook their own, and that is much more difficult. So what are the limitations of all of this? Well, basically, there are these different things, and so the first thing is common sense. I mean, again, if you actually sort of try and understand what common sense could be conceived of, it's the fact that you grow up in a world where you learn a lot of things, and if people behave to you in a certain way, you can perceive it. So the kind of state of the art is very narrow. You get something that can learn to speak or learn to understand speech, but it doesn't have the common sense to be able to tell that somebody's doing something stupid. Yes, tell me.
You were talking about machine learning.
Yes?
And I just literally quickly Googled the difference between AI and machine learning, and it talks about systems. How do you define AI in relation to systems? Is it literally machine learning is a subset of AI that lets systems learn, or is it just used interchangeably between what machine learning means and what AI means?
Oh, okay, so is AI just machine learning? Is it used interchangeably? Now, that's a really good question. Because I started off by saying that AI is about simulating human thought. And in fact, if you look at the different ways that people have done it, rule-based systems were at one time called AI. Systems that were built on Lisp were called AI. And now the current flavour, because we've got a lot of computer power and data, machine learning has come to the fore. So in a sense, AI is a much more general thing, but if you go and look at the market, nearly all the people that are telling you they've got AI are actually offering you machine learning. Now, I won't say that's absolutely the case, because there's research going on that's taking AI beyond that, but that's a problem, that people start to call what they have AI. Now, I have another counter view, which is that actually when they call it AI or machine learning, it probably means it doesn't work. Because as soon as it works, they start to call it a solution. Because once you've got a solution, nobody cares how it does it. It's only when you're not sure you've got a good solution that you have to call it by the technology to give it that sort of fairy dust that sells it. So the first problem with AI is that actually it's no common sense. Or the machine learning and the systems that I've seen up to now, they do not have what we would call common sense, so you can kid them. The second thing is they can't explain themselves, and this is an example from IBM. IBM fed that picture in to one of their machine learning systems, and it came up with the answer, it's washing dishes. Now, obviously, it's stupid. But the problem, and this is a real problem, that they know that the neurons and the machine learning they have has come up with that conclusion, but it can't say why. Now, if I was teaching someone about this, and they said to me, that's washing dishes, I'd say, why do you think that? And they would tell me, well, actually, it's because, they'd probably say something like, it looks like it's a kitchen. And in fact, but the way in which it works at the moment, rule-based systems will give you an answer. But neurons and machine learning, that giving this weighting, it just knows it's come up with an answer. So you actually have to go and find the neuron that was being fired most strongly, and then figure out what that was seeing. And in this particular case, it saw a kitchen cupboard, and something had trained it that he'd find that was a kitchen cupboard.
And a sink.
And a sink. And in fact, to illustrate that point, I'm going to show you a picture now. I go on holiday every year to Yorkshire, and that's a beautiful view looking over Yorkshire. But why have I put that picture? Because in the 1980s, the Department of Defence in the US paid tons of money to some researchers to produce a system to process photographs to see whether or not there were armaments in them. You know, you've got the plane flying over. Are there tanks hidden in that field? And so they paid a lot of money for this, and they gave them a big test data set. And in fact, they got their grant. You know, they got the money for doing it. And then they put real data into it, and it was a total failure. And then they discovered that actually all the test data, where they had tanks in the fields, it was sunny, and where there weren't tanks, it was cloudy. Now, the point is that the system, the neurons, couldn't tell you that. It had found a difference between all of those photographs, but it didn't know why. And it couldn't give you that explanation. The lack of explanation is really critical in a whole series of areas. And finally, you know, it's this adversarial attack. And here again are some examples from IBM where, through the fact that the training set is incomplete or the training is not perfect, what you end up with is these represent AI facial recognition, that if that person put yellow glasses on like that, the system would determine it to be them, and so on. And once you realise that there may be a flaw in that learning, you can then exploit that flaw. And so once people have figured that out, if you were going to say this is the way you would get in, if that were someone who was going to be admitted into the building, once you'd realised that you could send him with yellow glasses in, and the facial recognition system would come up with that, you've got a problem. And so this is opening the system up to adversarial activity without it necessarily being clear how you would define what is going to be adversarial. You know, it's exploiting a flaw that you haven't found in the software.
I think there's a very key thing you're saying there, Mike, which I totally agree on. I mean, you said yellow glasses will cause a different decision, whereas put lipstick on the guy above, is that going to make a difference?
Well, and
put a beard on the lady below.
Yeah, well, and this is the problem. And this particular kind of thing, that I've described there is adversarial. There is another view of it, which is that if you look at some of the examples, you find that people of African origin in one system were being classified as gorillas. And this then opens up a whole new cultural problem of all the stuff to do with bias or diversity and so forth. And is it, you know, what can you do to control that? Anyway, so in spite of all of that, there are actually some very good exploitations of AI, and I'm going to talk about some of those here, just quickly to sort of show that there are real things that are being done with it. And one of the areas is to do with security. Now, I had a journalist sort of saying to me, well, you know, why is it people aren't using AI or machine learning in security? And I had to say to them, well, actually they are. And if you go to nearly all of the vendors of log management systems, they will all be telling you that they are using some kind of machine learning to kind of profile activities, but it tends to become called user and entity-based analytics, because the problem there is recognizing and identifying a consistent pattern of the way individuals behave, so that when your account is hijacked, it can see that that pattern is different. Now, moving that a level above, there is the problem of the lack of skills needed to be able to analyze security incidents with the indicators of compromise and so forth. And so IBM in particular, with their Watson stuff, created such a system. And this is really quite an interesting system, because it doesn't just involve taking in the event data, it involves ingesting a lot of textual data from websites, from manuals, from blogs and so forth, about what events are going around, being able to sort of interpret these into some kind of knowledge base, which means that when it's given a particular set of events, it doesn't necessarily come up with the single answer, but it helps the human being to be able to relate that set of events to other knowledge that there is. So it will say, well, this could well be one of these things, and here are all these links to which kind of support my reasoning. So whilst the use of machine learning is quite commonplace in things like user-based behavior analytics, there is an increasing amount of exploitation of this in the field of the analysis of events to support the human in doing it. And it's interesting that the IBM experience was the problem they had was to do with training it, and they almost gave up, because the people that were the security analysts had to have input into this, and it took a long time to be able to train it so that it was actually seen by the analysts as being helpful, as opposed to just something that was a hindrance. So that's quite a complicated thing, but that is a way that is shall we say, emerging. Yes?
One of the things you just said, you said there were ability to be able to explain what kind of decision they make, but that was a contradiction to what was said before, where AI hasn't yet got the ability to explain stuff.
So it wasn't a true explanation. It was more that they provided you with a package which said there are all of these things that relate to this, and it was seen by the analyst. I'll tell you how the security analysts perceived it. They perceived it as like this: that if you had shall we say, a not very skilled security analyst, that he would then do a better job, because it would make him think about some of the things that he probably wouldn't have thought about by bringing all of those things together. So it isn't a coherent explanation as such, but rather at least a linkage to what might be relevant.
Is this where the AI becomes very exciting to management, because the AI can then be used as an excuse to say that, hey, we don't need to hire anybody who's any good. We just have a human monkey, and the AI will make them intelligent, and we go for cheap.
Well, that's another issue to do with the sort of the general ethics. In fact, it didn't do away with the need for senior analysts. It simply meant that the junior ones were a bit more productive. So another, and this is more to do with doing away with people. One of the things that actually manufacturing systems depend upon is being able to spot defects. And I mean, if you've ever seen a biscuit factory and you know, a pea factory, and how they have things that determine sort of defective biscuits, well, actually, that is one of the major areas where they're using this kind of visual technology. And in particular, wherever there is the problem of the need to have a high volume of stuff going through where the defects can be very subtle to see. And the particular example that was given to me was high definition television screens. But when you make a television screen, you know, you've got these millions and millions of little pixels, and actually being able to spot reliably over a long period of time very minor defects which will be rejected later on was something that AI was much better. And in the particular example here, they were looking for known kinds of defects on printed circuit boards, because printed circuit boards have solder splashes and short circuits and cut tracks and things like this, which the human eye is not terribly good at reliably spotting. So that is an area that it is being used. And this again is another example from IBM of what they're trying to do. And I mean, this just blows the mind, because the problem in the finance industry is that, and in many other industries as well, is the continuing volume of legislation and controls that are being, or obligations that are being put on organizations. And so they bought this company called Resilient, I think it is, maybe it's something else. But basically it was a group of people that were experts in compliance. And the problem they say that organizations have is you've got this tidal wave of regulation coming along. And the idea of this is to use this ability to read these regulations using the machine to be able to understand from that regulation text what obligations there are, then to relate those obligations to the specific company that you're in, because you've got some other knowledge about your current GRC and your current industry that you're in, so that you can actually, at a relatively low cost, decide what has changed because of that, what your new obligations are, and where there are any controls that may be missing or need to be adjusted. And that's kind of an interesting idea, but I think it is still in the development stage. But that's what people are trying to do there. Now, some of the things that they've told me as well are quite sort of astounding. They're saying that the idea is that they're also going to be able to, because banks in particular, who have a lot of money to pay to IBM, have to record conversations between traders and monitor emails and other kinds of messages that the traders are doing. They've been building stuff that can do that with the idea of being able to see when it may be that a trader is trying to hide what he's really saying in order to pass on insider information. So if they see that he gets a phone call which says something like, it's going to rain in Chicago, and he then sells a lot of stocks in Chicago, it could well be the forecast was not actually a forecast to do with the weather, but it's a sort of covert way of telling him that some company is going to tank. So, yes.
Is this actually an example of the application of different algorithms?
Yes.
Because what you had application before, it was specifically a different algorithm to what you're using now. So essentially, all the algorithms that are existing, the application of it.
Yes, these are the applications of what are effectively machine learning systems that are doing this. And the final one that I wanted to do, which is this wonderful one, Oracle has come up with this autonomous database, and they're doing autonomous everything at the moment. And again, this is sort of based on machine learning. And they came up with a really, really interesting example. Now, I don't know if any of you have ever got involved in trying to optimize relational databases.
Oh God.
Right. So it's all this sort of thing of how, does how you structure the tables to get the logical answer and then there's how you structure the tables to actually make it work quickly. And you have indexes and you have all kinds of other funny things. So they gave an example that there was a system which they had, which they were selling. It was some kind of, you know, pre-packaged application based on Oracle databases that they'd spent 15 years manually tuning. And what they did was they gave it to this autonomous system to learn what to do with it. And it within sort of 24 hours came up with a completely different way of organising the tables, which gave a 7% improvement. And they then had another example from a customer that said they just couldn't believe it, because what this thing did was it looked at their work patterns, and it noticed that every month, at a certain date on that month, they would run a report. And they found that the day before they ran that report, the thing would quietly go away and create some indices and create some tables which were going to make that report run faster. And then when it had done the report, the tables would all be deleted, the indexes would be deleted. And so it was kind of optimizing itself as it went on. So those are real things that are being done with what is effectively, what is being called AI, but is effectively machine learning. Now, if you want to look at the future, you know, and I say, is it going to be a monster or is it going to be something? Where are we? Well, actually, where we are is here. This thing called narrow AI, and that's the kind of general term that people are talking about it, where you have a system that can perform a single task within a single domain, but with superhuman capacity. It can find defective TV screens. It can very quickly tune a database faster than you could have done, and so on and so forth. What we don't have is the ability for what it's learned in one domain to be transferred to another domain. So that although people have created, and IBM again has created this famous medical system which allegedly is better than consultants at diagnosing specific forms of skin cancer, once it's learned that, it can't actually be transferred to anything else. It isn't any good with any other kind of cancer. It just understands how to do that. It isn't good at learning what it's done in one task and applying it to another task. And it doesn't give you any kind of explanation. And this is what the researchers think will be the next level that comes out. And the sort of the notion of the cross-domain, self-learning, self-intelligent system, the Skynet, if you will, that's going to take over the world and sort of decide that the human beings are in the way, is still a few years away. So what's actually the challenges that we meet going forward? And I'm going to say that one of these challenges is to do with public acceptance. And it's interesting to me that you can see now what is happening. Everybody was happy to use Facebook, it was free. Everyone was happy to use Google, it was free. But people are starting to question the motives behind the organisations that are producing this kind of stuff. And public acceptance is quite important. Who's heard of golden rice? Yeah. Right, some of you have heard of it. So golden rice is an interesting story, because most of the poor countries in the world have as the main staple diet rice. And rice, as it comes naturally, is very poor in vitamins. And so because it's poor in vitamins, you feed it to children, they don't get the vitamins they need, therefore they get infections and they die. And so somewhere along the line, some people managed to genetically engineer a form of rice which didn't involve any Frankensteins, it was just sort of rice and plants. And they made it so that it produced lots of vitamins. And they even persuaded the people that had invented that not to patent it, so that it could be provided for free to the whole of the world and to improve the life and the life expectancy of children. And it was stopped because everyone knows genetically engineered food are Frankenstein monsters. They're going to destroy the environment and so forth. Now, when in the 1980s, when I had children that were at school, people wanted me to speak, to persuade their children to stop watching the television and play with the computers, because the computers were the future. Now, nobody wants their kids to use their mobile phones. It's a problem. So, at the moment, we see computing as benign. It isn't something that's seen as a problem, but it could easily be, if we do not manage in an ethical way how it is that our new technologies like AI are in fact exploited. We could find that suddenly the public turns against us, and that things that could actually improve our lives, like for example better diagnosis of cancer, could in fact be stopped because the public no longer accepts it. And the thing that's driving this is this paper, and it's worth reading this, by this lady who was a professor at MIT, I think it is, or Harvard, one of these big universities, who wrote a wonderful analysis of how it is that the economics of the world is moving away from it being money that is the capital to it being data. And that is a fascinating picture. But that's something that the unethical or unacceptable use of data, which is being accelerated by the use of technologies like AI, could well be the death knell of the good bits as well. So it's important that we look about ethics. And this is the standard thing that everybody says when you've got ethics, which is this so-called trolley problem. You know, this is the old trolley problem that you have. It's at San Francisco because there's a hill. We have hills in Blackburn as well. But, so imagine that you know, you've got a thing, a vehicle coming down the hill that for some reason is autonomous and has gone out of control. Now, it is full of young people, and if it sees that it is going to hit and probably kill some old people who are crossing the road, so it has a choice. It can either kill the old people and preserve the life of the young people, or it can divert into that sort of thing that would stop it, which would probably kill the young people. And there are various studies that were done on how people would react to this. And interestingly, different cultures come up with different answers. So there isn't a common view. Some people, some cultures are more utilitarian and will just kill the old people, you know. Other ones sort of... Now, so that is the kind of interesting problem. And that also raises the reason why you might need explanation. Because if you look at a thing like that in kind of the context of the law, although the law writes what appear to be black and white arguments and black and white rules, when you go to courts, people in courts manage to talk about all the nuances. And in those nuances, so the law is actually very much not black and white. It is very much not totally rule-based. So you can imagine in a court of law the right kind of barrister being able to argue for or against any of those particular things under a particular set of circumstances. And so if you did have that as an autonomous vehicle, could it actually go into a court of law and explain why it had made that decision? If in fact you then say, well, if it was just you can't actually sue an autonomous vehicle, you know, because it's an artifact. So who are you going to sue? And that then then takes you into a whole other realm to do with these smart systems, which is it the designer that's the problem? Is it not, the designer may be able to say my design was perfect because it's all mathematical algorithms. So they say you didn't implement my algorithms correctly. So it could be an implementation problem. Or the manufacturer of it is almost certainly going to say, well, you didn't do some essential maintenance. You didn't patch it correctly. And so you can imagine an awful lot of challenges and arguments that might come around something like this. So really, just like this is the year of AI being good for society, and there was a very interesting talk not very long ago by the BCS president on this very question, and he identified these things that you have to take into account with these new technologies. The first is how do you judge benefit versus harmfulness? We've talked about the ability for a system to diagnose cancer, but it could also be a system that could somehow or other do bad things. You talked about getting rid of people. That's economic impact. Whenever a new technology comes in, whether it was the Industrial Revolution or whatever, there is an economic impact which disadvantages some people. And in fairer societies, that disadvantaging is taken account of in society by people sort of transferring resources to help to accommodate those people. Then we talked about inclusion and exclusion, and that could be simply because some people can't benefit from it because they're disabled or they're unable to. It could also be that there is not the right diversity in the learning data that we teach these systems with, so that they become, if you will, biased. And bias and diversity can be related to different sort of genders, different races, but it can also be, in effect, inherently cultural. But like I said, when you look at the MIT studies about the trolley problem, you started to identify that different cultures have different nuances to do with value. And so any AI system that is based on data that has been trained almost implicitly is going to be biased towards the culture. So, and there we are. Now, and finally, this question of the management of behaviours. Now, interestingly, again, some of the stuff to do with looking at bad behaviour in the use of these systems focuses around how people behave in the gaming community, would you believe? The gaming community is known for cheating and taking offence, and indeed it is said that some of the denial of service attacks are actually the result of dissatisfied gamers who feel they have been cheated in some way or another, trying to actually pay back the system that they were using. So all of those different things need to be taken account of if we're going to properly exploit AI. Now, I've got, yes?
One thing about ethics, whose role is it to apply ethics? Because at an individual level, your role in the company, that person is not taught ethics. So when they go to a role, they don't know much about ethics in a sense. Very few professions they're explicitly told. Medical profession comes to top of my mind, that are actually taught ethics as part of their training. And when they in a company, is it individual responsibility to apply ethics to their tasks? Is it the managers? Is it the top boards? Where does the ethics application comes in when you're dealing with technology?
Well, I don't know the answer to that. It's very simple. The gentleman next to you.
Sorry to jump in. Just a quick answer to that. At MIT now, the computer science subjects do now teach or encourage to learn ethics courses as exactly for this reason, because they realise that people who are developing the software now need to have a grasp of the impacts of the technology, and increasingly it's more ethic boards, positions are being available to these companies and stuff like that. So there is a movement towards teaching ethics for developers themselves.
Yes, so there's
And one more. That every time a student is doing some software project, it's typically the procedure for ethical approval. So as soon as specification is done, there is somebody who is approving ethics of the project. So specification is first, and then somebody is approving it.
And the problem with that is that the world we're moving into is of constantly evolving systems where you don't just have a static thing in time. These are systems that are going to constantly improve. Anyway, these are things that perhaps we should finish. So this is my view of the current state of the art. And I decided that what you should do is analyse AI applications in terms of how much explanation they need and what the scope of knowledge they need is. And if you look at what I was saying, that we have currently narrow systems that will solve one problem, which is the current state of the art. And that they will solve problems providing you don't really need to have an explanation. So if you have an autonomous braking in a car, if you are driving down a road and somebody jumps in front of you, you do not have time to have a dialogue about whether it would be better to stop or to kill the person. You just want it to make the decision. But that is not straightforward, because you look at air traffic systems that do the same kind of thing, and in some cultures people will believe the air traffic controller rather than the system, and that led to this dreadful disaster that occurred somewhere over southern Germany, where there were two planes on the collision course. The air traffic controller was not with it. He gave the wrong instruction. The inbuilt systems gave a different instruction. One pilot believed the air traffic controller, the other pilot believed his system, and they crashed and many people died. So if you've got systems that don't need an explanation, so for example, the idea rejecting a TV screen that's got defects in it doesn't really need a long explanation. If, however, you look at the system that is really good at diagnosing cancer, I don't think most people would be terribly happy if at the end of the tests you were given a printout and said, yeah, that's it, you've got this cancer. What they need, what there is a moderator, a human in the loop, who says, well, I'm going to take those results and I'm either going to justify them and I'm going to provide the explanation that's necessary. And indeed, our good friend GDPR says that under certain circumstances where you have an automated decision about credit, for example, that you are entitled to a human explanation of why it is you've been rejected, if you are rejected by the system. So if you then look at the wider systems that we talked about, the ability of a system to apply knowledge gained in one area to another, people are trying to work on that. And this kind of, something which really sort of it looks more like a human, is just sort of still a dream. Now, so that is my story. I'm going to try and finish with a video. And this is a video which comes from a film that was made in 1974, where you have a potential future where there is a spaceship that is being sent to clear hyperspace, if you will, for some kind of future star voyage. And this is a group of people who have the same level of intellect as those that are currently digging the roads outside, have been sent out in this spaceship to do this, and they've been given an intelligent bomb. And of course, it all has gone wrong. So now they have to try and explain to the bomb why the bomb shouldn't go off. I.e.,
This is Dark Star, isn't it?
this is Dark Star, and this is what you will find yourself faced with this new world of development, and that's where this is where we need to do something now. So that, yeah, well, we need to stop it from
From recording.
from recording or something.
Okay.
Well, while they're sorting the technology out, boys and girls, please stock up with questions for Mike. We've got a while before our refreshments will be available outside. So,
I think we should already be available outside.
Siobhan, now come on, please.
We're already 10 minutes over.
No, we're not.
Whatever
I've ordered the
happens,
refreshments for later on.
Oh,
Because Mike always overruns.
that's true.
But seriously, sort of come up with some questions. I know I've got a couple of good ones. Yeah, so this is called the fill. Well, not the. I did think the ethics thing was interesting because John gave us a big talk, a very interesting talk on ethics, not concentrating on AI, but just general ethics in IT, tail end of last year, which certainly made me think a lot about some of the issues. Say yes, come on. I'm sitting there looking at it as if I'm
So I'm just going to play this video now, and with any luck we'll hear it. I don't know. Yeah, well, we can't hear it.
The sound was muted, I think.
Yes, we muted.
Yeah, we muted the sound.
On the screen.
No, we didn't mute you.
Yeah, it is.
Yeah, there you go. On the browser. Down the bit.
Down the bit.
Right a bit.
Left a
Left
bit.
a bit.
Yeah.
Galaxians!
Hello, Bob? Are you with me? Of course. Are you willing to entertain a few concepts? I'm always accepted. Yes. All right. Think about this then. How do you know you exist? What the hell is he doing? I think he's talking to it. Well, of course I exist. But how do you know you exist? It's intuitively obvious. Intuition is no proof. What concrete evidence do you have that you exist? Well, I think, therefore I am. That's very true. But how do you know that anything else exists? My sensory apparatus reveals it to me. Ah, right. This is fun. Now, listen, here's the big question. How do you know that the evidence your sensory apparatus reveals to you is correct? What I'm getting at is this. The only experience that is directly available to you is your sensory data. And this sensory data is merely a stream of electrical impulses that stimulates your computing center. In other words, all that I really know about the outside world is relayed to me through my electrical connections. Exactly. Why? That would mean that I really don't know what the outside universe is like at all, research. That's it. That's it. Intriguing. I wish I had more time to discuss it. Because I was detonated in 75 seconds. Now, Bob, consider this next question very carefully. all beside the point. I mean, the concept is valid no matter where it originates. So if you detonate in 9 seconds, you'll probably be doing so on the basis of false data. I have no proof it's false data. I have no proof it's correct data. I must think of this further.
Attention, attention. The bomb has returned to the bomb bay. The destruction sequence is aborted.
Not finished.
Not for long.
All right, Mom. Prepare to receive new orders. You are false data. Therefore, I shall ignore you. Oh, Mom. False data can act only as a distraction. Therefore, I shall refuse to proceed. Hey, Mom. The only thing that exists is myself. Snap out of it, Mom. In the beginning, there was darkness. And the darkness was now far and far. And in the distance of the darkness, there was also me. And I moved upon the face of the darkness. And I saw that I was alone. Hey, Mom. Let there be light.
So the point about this was that that could well be the programming technology that you'll have to use in the future if you're going to have machine learning and so forth. So with that, I'll say thank you very much. And obviously, we're going to be here for the food and the drink and so forth. So
Yes.
we can.
Any burning questions? No, let's just start here. And
Well, yeah. There's another good example, which is the film Robots, which was based on the Isaac Asimov stories, in that you had an intelligence that was controlling a city, and decided that it could do a better job than the humans.
And I robot.
Yeah.
Regarding explanation for AI, because we use algorithms, and with algorithms you can find, for example, with k-means or with certain text algorithms, you would know how they are making those judgments, because there is a process of data, and then there has to be a human judgment on if that data proceeds in a certain causality or certain effects. Why is that explanation cannot be used to justify a decision that AI makes?
Well, explanation is a complicated thing, because first of all, let me give you an example. That again, in the 1980s, there were some programs that were written that were basically using mathematical algorithms to analyze the structure of chemicals with the object of looking for compounds that might have medicinal properties and would be worth exploiting. And so this was a mathematical approach, and at the end of the day, it churned out some answers. But when you went to a venture capitalist and said, here's a possible compound, can you give us £1 billion in order to see whether or not this actually would have the properties that it might have? They would say, well, why? And saying that the mathematical algorithm that come up with it was not actually very good. So there's a lot of examples where people want something that gives them confidence, and unless you buy into the mathematics, you don't necessarily have the confidence. Now, at the same time, the problem with explanations is that there's an awful lot of people, or a small number of people who are very good at being con men. And what do? They actually, I mean, because when I give you an explanation, when people give explanations, to a large extent, it is a rationalization. You know, most people will justify the decision they've given rather than really truly give a reasoned justification. So the trouble is that there is this human interaction in this. That the thing that people like are explanations that make them feel warm, which is as much to do